get started on my talk tonight. Tonight I'm going to be talking about electrochemical detection of single entities. You could also call it single particles. The reason I went with entities is because there's a few different variations on it that are not, it's not limited to just particles. That happens to be what my work was, but as I'll discuss, we're not really quite limited to just that. And so I kind of wanted to make the title a little bit more inclusive to reflect that. As I said, my name is Dr. Ben Meekins. I'm a research assistant professor at the University of South Carolina in the chemical engineering department. My background is in photoelectrochemistry and electrochemistry, and in particular, catalytic processes to generate energy in various ways, electricity, hydrogen, conversion of waste streams into higher value chemicals, and both at a fundamental level and at an applied level. And so this is actually some older work of mine from about 2.5-3 years or so ago. That was a continuation of some work that I had started as a postdoc at the University of Texas. And so I was able to finish it up and get it published, and I thought it was some really interesting work. So the history and motivation here of nanoparticle collision detection, first of all, it comes in many forms. As I said before, the reason I kind of changed the title a little bit is to reflect the fact that it's not just nanoparticle collisions that you can detect. You can actually detect the presence of molecules and things like that in solution. And so you can do all kinds of different things. But it is useful for nanoparticulate measurements because it can provide information on individual particle catalysis versus the larger ensemble activity measurements that you make when you do sort of larger scale experiments. So even if you use, for instance, a catalyst deposited on, say, a rotating disc electrode, that will give you some very detailed information, but you're still looking at an ensemble measurement. An ensemble in this case means a collection of particles of different sizes. So the advantage here is that you can actually see single particle collisions and actually and pull out information about a particle, and you can look at things like very careful size dependence. You can look at reaction kinetics. You can look at even the stability of the catalyst itself. And so that's very useful information in terms of understanding the fundamentals of your reaction. So let's say you've invented a new catalyst. You put it into a batch reactor, and you notice that generally it works pretty well, but over time you see this consistent, let's say 20% loss of activity. And you study your catalyst, and you look at, you do X-ray photoelectron spectroscopy, and you do X-ray diffraction, and you can't tell any actual difference for the most part. But you could come back here and do the single particle catalysis and find that any particles that are less than a certain diameter will carry out the reaction, but will then deactivate for some reason. And so once you know that, you can start trying to figure out what the deactivation mechanism is, and if it's something that you can fix, you fix it, and if it's not, then you try and make sure that your catalysts are larger than that threshold size, and then you don't have to worry about it. There are two sets of researchers who are generally credited with sort of being the first to publish in this area. One was a scientist, I believe in Czechoslovakia, whose name is Mika. Published in 1957, and then two other researchers, Jones and Kay, in 1969, were kind of the other researchers who published in this area. In more recent decades, really, about the last decade or two, two main groups have really dominated this area. The Bard group at the University of Texas, and that's Alan Bard. He's kind of known as the godfather of electrochemistry. And then the Richard Compton group, and I believe he's at the at Oxford University in England. Those two groups have done a lot of work. Bard's group tends to focus more on the not applied side necessarily, because it's still very fundamental work, but on more of experimental research. The Compton group incorporates a lot of theory into their work, and so the two together are very complementary. The Compton group does experimental work as well, but they also add in a lot of theoretical work on things like the thermodynamics of the catalyst, of the collisions, aggregation models, things like that. So it's like I said, it's a very complementary work, and it served as a great background for me, and I'll talk a little bit about that when I get to those parts in my work. But the biggest motivation behind pushing this is not just a fundamental study, but this work can also be used to detect single molecules of extremely dilute solutions. And we're talking about femto to attomolar concentrations. And that's a really big thing, because it's not hard to imagine if you're looking for early indications of a disease, or trace amounts of explosives, or something like that. Most detection methods now, require at least micromolar concentrations, and that is a very small amount, but you have to be very careful, because those detection limits are not that low, and so this represents a way to go down to even smaller concentrations and still have solid detection limits. All right, so let me talk very briefly about the particle synthesis. It's not so much the synthetic method that matters very much, but there's some important factors that have to be kept in mind. So a couple of things here. First, my work was the first work that I'm aware of to have been published on nanoparticle collisions in non-aqueous media, at least in a continuous phase. There were a couple of papers on emulsions in water. So it was an organic phase that was, that had surfactant on it and allowed an emulsion to be formed, where these organic globules basically were suspended in water. But in my case, it was a mixture of toluene and acetonitrile, so it was purely an organic phase, aside from whatever small amount of water got taken up by the solution. So that changes two things a little bit. If you're working in aqueous phase, nanoparticle synthesis is very easy. There are literally hundreds, if not thousands, of papers on nanoparticle synthesis of any number of metals in aqueous phase. And that allows you also to use a lot of different ligands. And the ligands matter, because the bulkier the ligand is, the more difficult it is to actually observe a collision. If the ligand is too bulky, the particle never gets close enough to actually carry out a reaction and be in electrical contact with the electrode. I'll talk a little bit more about that coming up. So you kind of have to choose very carefully. But in aqueous solutions, you have a number of ligands available to you that are both small and also very charged, which allows you to synthesize a very stable solution of these nanoparticles. In non-aqueous phase, you're a little bit more limited, because you can have, you don't really want to have a charged ligand, because that will lead to agglomeration and crashing out of these particles from solution. And so in my case, I use what's known as the Brust method to take a gold salt from the aqueous phase to the non-aqueous phase, and then add propane thiol, which is a non-polar ligand, but the sulfur group there will attach very strongly to the gold, and then add sodium borohydride as a reducing agent. And so what you end up with is a gold nanoparticle that's very small and is capped with these propane thiol ligands. And so this particular solution, once you remove the aqueous phase and wash the non-aqueous phase with water to make sure you've removed all the excess salt, the nanoparticle suspension or nanoparticle solution is actually very stable. It was stable on the order of months without any significant size changes or aggregation. And so that was kind of the important first step. So now I have a gold nanoparticle solution with a short carbon length ligand, and so now we can get to the experiment. So this is what a very, very simplified version of what the experimental setup is. So we would have an ultramicro electrode tip that was handmade. So this is a 25 micron platinum wire. Initially, we have gold nanoparticles floating in solution. We have tripropylamine, which was the probe molecule used here. And what we want to try and do is oxidize tripropylamine to its oxidized form. And the way we do that is we poise the potential at a place where the platinum ultramicro electrode is inactive and the gold catalyst will be active. So in this case, I actually went pretty far back to about 0.35 volts. I wanted to ensure that my background current, that is when just the current of the platinum ultramicro electrode itself, was very, very low. And by doing a lot of grounding work, including actually running a wire across the lab to a water pipe, I was able to get the noise of the system down to half of a picoamp. And that ended up being very important because a lot of the steps that I'll show you in a little bit were on the order of 1 to 2 picoamps. So it was important to get the noise level in the electrical signal as low as possible. That actually included even mounting the Faraday cage on a swinging platform to try and eliminate vibrations, as well as grounding both the Faraday cage and the potentiostat to that water pipe that I mentioned. So all of that had to happen. You could not have people walking by. All of that would result in fluctuations in the measured current. So once you inject gold nanoparticles into the solution, what you have happen is they diffuse around, and ultimately what you hope to have happen is one of them collides with the ultramicro electrode, and now the tripropylamine oxidation proceeds. So on the platinum, it's not favorable at the potential that we choose, but when the gold connects, it is favorable on the gold particle, and so we observe a change in the current that occurs. So there's really 3 possible responses depending on what you're doing. First, you could have a step function occur, which means that a particle hits and sticks and just continuously, it basically increases the amount of current that is passing, meaning that it's catalyzing a reaction, and that just continues. You can have a step decay function, which means that it can mean a couple of different things. First, it can mean that the particle hits, performs some catalytic reaction, and then the particle itself dissolves. It can also mean that a particle hits and then is somehow, maybe continues to stick but is deactivated. So an example of this would be if you had a hydrogen evolution catalyst that hits and sticks, and it starts to evolve hydrogen from a proton solution, but the bubble sticks on the catalyst. If the bubble is big enough, it can actually block the catalyst from any further reaction, and what you observe is the same as if the catalyst was completely deactivated. So until that bubble falls off, it will deactivate the catalyst. And the last thing that can actually happen is you can actually generate a step down function. So there are times where you actually don't want to catalyze a reaction, you want to observe a blocking mechanism. So for instance, you could try and detect a molecule of DNA, a particular chemical species, by choosing your ultramicro electrode material such that it is actually very catalytically active, and once one of those other molecules attaches to the surface, that catalyst site is blocked, and what you actually observe is a decrease in the current that's flowing, because now your catalyst has less active area, and so you have less overall current. This is not as often used, but it is a very valuable tool. It's been used, for the case that I just mentioned, where you're trying to detect certain molecules, but it's also been used to determine things like the rate of first collision, or the time of first collision, the rate of different sizes of the rate of diffusion of different sizes of particles, and things like that. So it still has a very useful function. All right, so there are a few things that we can learn immediately from the steps. And so there's three equations here. The equation in the top left is the flux of the particles that you inject to the electrode. So these would be the nanoparticles, in this case gold nanoparticles, that you are using as your catalytic material. And so this flux is just 4 times the diffusion rate of the nanoparticles, which you can calculate assuming a certain radius, multiplied by the concentration of the nanoparticles. Again, you know how much you started with, you know how many atoms of, for instance, gold are in a nanoparticle of a particular size, so you can back out what your concentration is. And then finally, you have R naught, which is actually the radius of the ultramicro electrode. And if you think about it, it makes a lot of sense. If your electrode diameter is huge, then there's a lot more space for a collision to happen, and so it's much more likely to happen, it's likely to happen at a higher rate. Versus if it's smaller, you expect that rate to be much lower. Similarly, if you have fewer nanoparticles in solution, you expect that flux to the electrode to be lower. And so, the equation makes a lot of sense. You can also back out the frequency of collisions that you expect to see happen. And that's just the flux of particles to the electrode multiplied by Avogadro's number. And so all that gives you is the number of atoms per second, or the number of collisions per second, that you predict to have happen based on the diffusion of your nanoparticle, the average diffusion rate of your nanoparticle, the concentration, and the radius of your electrode. And then the last thing is you can actually predict a step size. So if you go back to this step function here, whether you expect a step function, step decay, or a step down, you can predict what the size of this point should be. So from your baseline to your maximum point, you can predict what that should be with this equation here. So it's just because it's in my case, a spherical particle contacting a flat surface, there are some factors that you have to add in. In this case, it's the 4 pi times the natural log of 2 times n, which is the number of electrons in the reaction, times F, Faraday's constant, the diffusion coefficient of the redox material, so in this case the tripropylamine, and the concentration of the redox material, again the tripropylamine. And now this A is the radius of the nanoparticle itself, because that gives you that's a measure effectively of the active surface area. And so you can see, if you have a slow diffusing probe molecule, you'll see a lower current step. If you have a smaller particle, you'll see a smaller step. If you have a huge particle, you should see a very large current step, and that typically is what happens. So first thing, of course, is you need to characterize nanoparticles, because a lot of this depends on what the size, at least the average size of the nanoparticle is. The diffusion is calculated. The diffusion of the nanoparticles is calculated based on the radius, which affects the frequency of the collisions you expect. And then, of course, the step size that you expect to see is also dependent on the radius. And so it's not always advantageous to have very, very small particles, depending on what you're trying to see. In my case, because of the synthesis method and the medium that I'm working in, it actually, we're kind of limited. Excuse me. In aqueous phase, you can make either very small particles on the order of 3 to 8 nanometers, or very large particles going up to 50 to 100 nanometers. Larger particles are much easier to work with. They tend to be more monodisperse, meaning they all tend to have roughly the same size. But of course, going back to this equation, the expected current step size is going to be much larger, which means it's easier to detect, which means you have a little bit more room for error in your background measurement. In my case, though, the particles were generally in the 1 to 5 nanometer range in terms of diameter. And you can see from this transmission electron microscope image, there is clearly some aggregation that happens. So you have some particles that are larger, but for the most part, we generally have spherical particles that are in the 1 to 5 nanometer range. This was confirmed with some dynamic light scattering data that I collected as well. And that one actually gave a very tight spread of about 2 nanometers in diameter, plus or minus half a nanometer. And again, one of the assumptions that we make is that the nanoparticles are spherical. In this case, it looks to be a pretty good assumption. There's nothing really oddly shaped. They're not squares, triangles, something else. So our assumption of spherical particles is reasonable. So first thing we need to know is, what does a detection of a collision actually look like? So the steps will be of varying size because the particles will be of varying size, but those can be correlated. The frequency of the steps, as I showed you with the equation, is determined by both the diffusion rate and the concentration of the nanoparticles. And what that means is we need to choose, the diffusion rate of the nanoparticles is based on the size. And so we can control the size somewhat, but once we know what the sizes are, we need to choose our concentration of nanoparticles that we add very carefully. If we have too high of a concentration, we're going to have several steps happening at even the fastest detection rate that we can have. And what that means is we can't tell one collision from another. So if you have 5 particles all hit at the same time, you're going to see a huge step, but you don't know whether that step was caused by one single particle that was very big, 2 particles that were very, slightly smaller, or 5 individual particles that all happened to hit within the same minimum measurement window that you had. So we generally, the rule of thumb is generally that you choose your concentration of nanoparticles such that your expected frequency is less than 1 per second. You could probably get away with a slightly higher frequency rate, but we choose that because it gives us some leeway in terms of the measurement. So if something wonky happens, and the frequency ends up being a little bit higher, it's okay. We're still, our measurement speed is typically on the order of milliseconds. So if we're aiming for less than 1 collision per second, that gives us a lot of wiggle room to detect, the collisions that are happening very close together without them landing on top of each other, such that we can't differentiate. And so using the equations on the previous slide, for an average diameter of 2 nanometers and using a concentration of 10 millimolar of the tripropylamine, the predicted step size for a 2 nanometer diameter particle would be about 7 picoamps if the process is a 2 electron transfer, which is what was predicted based on my literature review. At least in aqueous solutions, the tripropylamine typically went to a 2 electron oxidation and ended in a neutral species that would not react any further and would also not undergo a reduction. So it was a one-way reaction, but with two electron transfer steps. And so the figure that's here is showing you sort of a baseline measurement. So this is what it looks like if I apply 0.35 volts with a platinum ultramicro electrode and no gold nanoparticles at all. So the only thing in solution is 10 millimolar of tripropylamine and 25 millimolar of a supporting electrolyte, and that's it. And so it should be very clear here that there are no steps at all. This is just a nice smooth line. It shows a decay over time, which you expect. Whenever you step a voltage, you're going to see an increase in current immediately. But if there's nothing to sustain that current, then it will drop off very quickly, as you see here. So when we actually add gold nanoparticles, this is what we see. There are very clear staircase step properties to this. And so that's what we expect to see. So this tells us immediately a couple of things. One is we can look at the step size. So using this one, for instance, we can see it goes from just below 0.5 nanoamps to about 0.51. And so that's actually about a 10 picoamp step. That's just as one example. But the more important thing here is that the step is it's not a transient event. There's a step and then it's relatively flat after that. And so what that tells us is that the particle is hitting and sticking and not coming back off. Nor is it hitting and then dissolving or something like that. And so those are two very important things that we kind of have to keep in mind, because it is possible, especially with small nanoparticles, to have them actually be broken up during the course of the reaction. So over the course of multiple different runs, I believe there were 4 or 5 different runs that I did here for replication purposes. All of that is kind of summarized into this current step distribution. There's 973 total events. I set the cutoff at 1 picoamp because my noise level was about half a picoamp. I wanted to ensure that my signal to noise was at least 2, and so any current steps that were below 1 picoamp were disregarded because I couldn't guarantee that the signal to noise was strong enough. But obviously at 973 different events, that was more than enough to start doing some analysis of what actually happens. And so it turns out that there are 2 different ways that you can fit this. The first is with just a normal Gaussian distribution, and basically what that assumes is there's not really that the particles are hitting in a way that their size distribution is a normal Gaussian, which you would kind of expect. If they're just hanging out in solution, nothing's happening between them. As synthesized, you expect a Gaussian distribution, and that's what you expect to see in terms of the current steps if there's no interaction between them. On the other hand, and this was some of the theoretical work that the Compton group had done in combination with some of their own experimental work, if there is interaction between the particles, so if there's, say, this equilibrium between aggregation and segregation of the particles, what you actually expect to see is something more like a log normal distribution. So the same kind of peak, but with a longer tail. And as it turns out, that's what I observed here. You can see, both the Gaussian and the log normal give decent fits. The R squared of the Gaussian is 0.983, but the R squared of the log normal is 0.998. So it's clearly much better. And that's also reflected in the chi squared value. For the Gaussian, it's 27.9, and for the log normal, it's 3.41. And you generally you want the chi squared to be as low as possible. So what we find is actually that there's a bimodal log normal distribution. So there are peaks at 2.5 and 5.7 picoamps. And it's interesting to note that was true for both the Gaussian and the log normal distributions. So even though the Gaussian didn't fit it as well, the peak positions were the same, which was kind of interesting. But so, like I said, what this tells us is that there is aggregation happening, and that was kind of already known, but it was nice to have it confirmed. And I'll talk about how we knew there was already some aggregation going on. So this is the first way. In the course of some of the experiments, and actually I think it happened in every single one at some point, it would be going along showing relatively small steps, and then all of a sudden you would see a step that was a nanoamp or larger. The reason it actually goes down here and flattens out is that it maxed out the current range of the potentiostat. And so it could not measure a current value higher than this. But what we see is that it also comes way back. And so this tells us a couple of things. First, that either a single huge particle or a mass of particles all hit the electrode at the same time. And it resulted in this massive current spike that you see. The fact that the current came back down, however, suggests, and the fact that it came down functionally as a step, it curves off a little bit here, but there's a huge jump back. It suggests that the particles fell off of the disc electrode, and so that means that they were not tightly bound. But the if you want to call it like a baseline compared to where it was before the step, it is still increased. So it suggests that most of the particles fell off. Some of them stayed stuck and bound to or attached to the electrode. But what's also interesting is if you compare the noise in the current measurement before and after this spike happens, it's very clearly more jagged after the spike, after the aggregation hits and comes back off. And so what we can take away from this is that after this aggregation happens, there's all these particles. They're in solution, so they're not actually in contact with the disc electrode, but they're very close to it. And although the general trend is that they hit and stick, there's at least a few cases you can see here where there's a step, but then there's a step back. And so that suggests that these particles are hitting and then falling off and hitting and falling off. And what's interesting about that is it changes. If you look at the frequency of the collisions, we predicted a very low collision frequency of about 0.07 per second, and what we actually got was up to about 0.7 per second with this aggregation happening, which resulted in a mass of particles near the electrode that effectively provided almost an artificial increase in the rate of collisions. And so we also could see the aggregation. This is the dynamic light scattering I talked about. So this is the freshly prepared gold nanoparticle solution. You can see the average diameter is 2 nanometers plus or minus about 0.5, 0.6 nanometers. Very tight distribution. On the other hand, when I added the gold nanoparticles to the electrolyte that I used, which is 10 molar tripropylamine and 25 millimolar tetrabutyl ammonium hexafluorophosphate, after an hour in that electrolyte, the size changed dramatically, literally 2 orders of magnitude to about 430 nanometers plus or minus 30 nanometers. And so that kind of makes a lot of sense based on what we saw here. Again, in every single one of my trials, we saw this. At some point, there was a big step like this. The exact time when it happened would vary, but there was pretty much always one that happened. And in this case, I didn't do any time steps between fresh and 1 hour. This was mostly to see if the aggregation could be observed, like if it was a stable aggregate, basically. And it turns out that actually is the case. After 1 hour, you do have very stable aggregates. Actually, this was not crashed out of solution. These were very happily, still suspended in the solution, but the aggregation was there. And basically, what happens is when you add both the tripropylamine and the supporting electrolyte, the tetrabutyl ammonium hexafluorophosphate, you reduce, because the propane thiol ligand is not charged, the repelling force is not very strong, and so as soon as you add a supporting electrolyte that can even provide a little bit of ionization, the particles are going to want to come together, and so you end up with, again, it's an aggregate, it's a stable aggregate, but it's an aggregate nonetheless. And so this explains the huge steps that we see, or even the ones that are larger than our predicted step size. But one thing that was interesting is, if you recall, the predicted step size for this was 7 picoamps. And about 3/4 of the steps that were measured were less than that 7 picoamps, which means that we did something wrong. Well, not necessarily, we didn't do something wrong, we predicted incorrectly. So kind of going back to what does it all mean, like I said, we demonstrated nanoparticle collision detection in a non-aqueous continuous phase for the first time, and this has some advantages over aqueous solutions. A couple of things. One, it opens up this detection strategy to molecules and chemicals that might not are not soluble in water. But it also, non-aqueous solvents in general have much wider electrochemical windows. So they can, water has an electrochemical window from about 0 volts to 1.3 volts because Outside of that, you're producing you're producing hydrogen and oxygen through the breakdown of the water itself. Acetonitrile and toluene, on the other hand, have windows that are, anywhere from 3 to 5 volts wide, and so you can apply much stronger potentials and drive different reactions than you would otherwise be able to in an aqueous solution. We were able to observe and describe aggregation behavior based on the current response, so we could just total up all the current steps and observe the large steps and tell that there was some kind of aggregation going on. As I said, the current response actually tells us that our assumptions were flawed. We can be reasonably confident in the diffusion coefficient. We can be pretty, we know what the concentration of both our nanoparticles and our probe molecules were, but one of the big assumptions that we made was that the oxidation of tripropylamine was going to be a 2-electron process, which should have given us a step size of about 7. But our majority peak in terms of the current steps was around 2.5 to 2.6 picoamps, which suggests that it was more likely to have been a 1-electron process. The other interesting thing is that there was that secondary peak at about 5.9 picoamps. And so what that suggests actually is, even though there was some large-scale aggregation happening, almost all of our collisions were either monomeric, meaning it was a single nanoparticle actually hitting, or dimeric, which means that there were 2 nanoparticles. Whether they were actually directly interacting with each other or not, you can't really say, but it means that they were hitting at the same time. And so so that was kind of an interesting behavior that you would not necessarily predict to have happened, but it happened very clearly. And so that's great. That's a lot of really interesting fundamental research. And so the question ultimately is, well, great. So what? What can we actually do with it? It turns out there's a number of things that you can do directly with this technique. You can design a nanometer scale electrode. Traditionally, to do this, you have to take a metal wire, start out with one that's already very small, heat it with a laser, and then pull it very, very quickly while it's in a glass sheath, and hope that you pull it in such a way that it both stretches out and becomes very thin, but also that it doesn't break either the glass sheath that it's on, it surrounds it, or that the wire itself doesn't break before you've reached a satisfactory diameter. And even with all of that, you're lucky if you get a nanometer scale diameter. You're lucky if you get a diameter that's maybe 50 nanometers. With this technique, a couple of colleagues of mine from the University of Texas actually developed a way to take a relatively small tip to start with, but then put down an insulating layer of titanium dioxide, and then reduce via tunneling a single platinum nanoparticle. And you can actually see there were 2 different variations on this. In the first case, they put the insulating layer on, but kept it thin enough, about 1 to 2 nanometers, such that it completely inactivated the disk electrode, but when a metal nanoparticle came into contact, it established a tunneling junction. And so you had a metal insulator metal junction where the only place that electrochemical activity could happen was on the platinum nanoparticle that was attached to the electrode tip. And so they were able to demonstrate that they could do that. In this case, it was about an 80 nanometer particle. But here, what they actually did was put the insulating layer on again, and then electrochemically reduce platinum salt, the platinum tetrachloride, onto the insulating layer via the same tunneling mechanism. And in doing so, they could get platinum particles that were as small as about 10 nanometers in diameter. And again, because the rest of the tip, this disc area here, all the rest of that is insulated. So there's no electrochemical activity happening here at all. The only place is on this small nanoparticle. And so what that means is you all of a sudden have this very, very, very sensitive tip. The background current is exceptionally low, And any collision that happens with that single nanoparticle, you're going to know it. You know, it will cause a very clear change, and you know that you've effectively increased the sensitivity of your electrode by orders of magnitude. The other interesting thing, and this is a similar reaction, is also from a colleague at the University of Texas. You can actually determine the number of atoms needed to activate a cluster for a reaction. So this was a guy named Jeff Dick. He took an ultramicro electrode and started slowly reducing different metals. So I know he's done it with platinum, copper, gold, and I believe nickel as well. And so what he would do is add very, very small amounts of a metal salt, poise the potential where it would lead to a reduction of the metal salt, and that metal salt would subsequently produce hydrogen gas. And what he was able to determine is based on transient events where the hydrogen, where the cluster would form, hydrogen would start to be evolved, and then the bubble would sit on the cluster and stop its catalytic activity. He could determine based on the size of the step and some calculations for what an individual atom would do, he could figure out how many atoms were actually present in the cluster. And so he could find that for different metals, you had a different minimum number of atoms that were necessary. So platinum, I believe, was 5 atoms. I think nickel was like 7, copper maybe was 7 or 9. But it was, it's not the exact same number of atoms to achieve this catalytic reaction. And so it's easy to imagine this being applied to other reactions, where you could figure out exactly how much of your catalytic material you needed to have. There are also detection things that can be done. So in this case, they were detecting single phospholipid vesicles. They were actually looking at this via a blocking mechanism. So every time the vesicle hit the surface, it would block active catalyst area, and that would result in the decrease in the current. And based on the size of that decrease, they could tell what the size of the vesicle was. They have also done a bunch of work with emulsion reactors. In this case, they actually were conducting reactions in an attoliter emulsion reactor. So again, this gets back to the detection at very, very, very low concentrations, where you can selectively look at reaction kinetics and things like that, as well as diffusion of reactants within this emulsion. You can have the emulsion hit and see how long it takes to consume everything that's inside the pocket. And so that gives you information not only on the size of the pocket itself, but how quickly your reactant inside of it diffuses to the surface to actually carry out the reaction, and how long it takes to consume everything in there as reflected in a transient. And so you can actually fit that and extract information again about the kinetics, about the diffusion rates, and even about how much of your reactant was present in the reactor itself. And so again, these are all, a lot of this is very fundamental work, but it's pretty clear to see that it can have big ramifications for, it may be a specialized application, but it's an application nonetheless. And even the principles that are involved here could be utilized in less specialized equipment, things like this metal insulator, metal junction, and techniques like that. Again, determining the number of atoms needed to activate a cluster is important, because that gives you some strong information about how the reaction itself proceeds, and what's necessary for it to proceed. And with that, I would like to say thank you to everybody for coming out to listen to the talk. And I will be happy to entertain any questions that you have at this point. There is a paper associated with this. It'll be posted with the YouTube video that will be posted after the stream is done. So I'll include a link to the paper for anyone that might be interested as well. And with that, I will open the floor up to any questions that anybody might have.